shapes. So basically what this boils down to is a theory known as VESPER, or valence shell electron pair repulsion, which is a really complicated way of saying electrons are negatively charged and they repel each other. That's it. That's all it means. We know electrons are negatively charged, and if a group of electrons in space come close to another group of electrons in space, they're going to repel each other. That makes sense, right? And so what we're going to learn is that in a molecule, basically all the electron groups, and when we talk about electron groups, we're talking about lone pairs and bonds. Any group, any place in space, an area of space that has electron density in it, like a lone pair or bonding electrons, are going to move apart from each other to try and reduce that repulsion as much as feasibly possible. So if you have a central atom with an electron pair with two electron pairs, they're just going to move to 180 degrees. That's going to be linear because that's as far apart as they can get, and so on and so on and so on. So we'll show how you build a model based on the Lewis structure, and then by looking at that, you can predict what kind of structure it's going to form. And then finally, once we have a shape and we understand how those electron clouds are situated around individual atoms. Remember, we talked about this morning. If one atom is more electronegative than another, it pulls that electron density a little closer to itself. So if we add that to the shape, we can determine whether or not a molecule is polar or whether it's nonpolar. So each group of valence electrons, like I mentioned, and a group is any group. Lone pair, double bond, single bond, triple bond, they're all considered one group. Why is that? Because they're all localized in space. So if I have, for instance, if I have a carbon-oxygen single bond, between them, there's a density of electrons, right? And so we call that an electron group because in space, there's a group of electrons. Well, what if it's a double bond? Okay, now I've got twice as many electrons in between that carbon and oxygen. Basically, it means the density is now twice as much because where there were two electrons between them, now there's four. It's still a single group of electrons. There's just twice as many of them. And so my density is higher. Well, what if it's a triple bond? Okay, that's even more density in between them because now I've got 6 electrons. But notice that they're all in between the carbon and the oxygen. They're all in relatively the same space. There's just more of them. So we consider this one group. This is also one group, and that's also one group. Why? Because they're in the same space. They're directly between the carbon and the oxygen. That's why we call them one particular group. So they're all single groups, but we will see that they have different effect on shape. Why? Because there's 3 times as many electrons in a triple bond as there is in a single bond. And so there's a lot more charge density in that one space. So it is going to repel other groups much more than a single bond would. And I'll show you some examples of that. So there's really only 2 things we're dealing with: bonds and lone pairs. That's it. Those are the only 2 groups of electrons we're really dealing with in this situation. So here's what the basic shapes will look like. Like I mentioned, if there is a molecule with a central atom and then an atom on one side and an atom on the other side, and it only has bonds on one side and bonds on the other side, that is going to be linear. Why? Because this group, this density of electrons on one side and this density of electrons on the other side repel each other. And so the way to avoid repulsion is to get as far apart as possibly can. And the greatest distance that they can have between each other is in a straight line. That is as far apart. Let's say my thumbs are the two atoms. That's just the most distance they can get from each other. If I move just slightly, notice my thumbs are closer together. Same as if I bend this way. Now they're slightly closer together. This is as far apart from each other as they can possibly get. If I have one, two, three atoms around the center, there's no lone pairs, there's only three regions of electrons. 1, 2, and 3. Well, if the greatest distance they can have apart is 120 degrees in this sort of triangle shape. That's as far apart as they could get from each other. Because the minute, just like with the single bond, the minute you bend in either direction, they get closer to each other. So if I bend up a little this way, they get closer. If I bend down a little this way, they also get a little bit closer. So that is also in a plane, but instead of 180 degrees, they're now 120 degrees in a triangle. That's as far apart as they can get from each other. So interestingly, these first two are basically two-dimensional shapes, really. They're both flat. The linear is flat, and when we have three groups, that's flat also. It's when we introduce to 4, 5, and 6 and more that we get these three-dimensional shapes. And the first one that we'll see quite frequently is this tetrahedral shape. So we have 1, 2, 3, 4 around the central atom. So now there's 4 electron groups. Now again, it could be 4 atoms, it could be 2 atoms and 2 lone pairs, 4 different groups. They form this tetrahedral shape, this sort of tent shape. And that is the way for those groups to get as far apart from each other as they finally can. And this is one of the numbers that you're going to want to remember. It is in the table, but it's a number that will come up more and more frequently. 109.5 degrees. What does that mean? That is the angle between these groups in space. 109.5. So if you have a perfectly symmetrical tetrahedral molecule, like for instance, methane, the bond angles between each of the carbons and 2 hydrogens, they're all exactly 109.5 degrees. Precisely, because that is the maximum distance those hydrogens can be apart from each other. When we start throwing in lone pairs, that changes the angles. Now, when we have 5, we have basically what looks like the trigonal planar, the 3, but stretched out. So we've got 3 around the outside, and then 1 on the top and 1 on the bottom. So there's basically 2 different bond angles. There's the 90 degrees from the top and the bottom to those circling the middle. And then there's 120 degrees between those 3 groups circling the middle. And we call that trigonal bipyramidal, because there's basically looks like 2 pyramids on top of each other. And then when we have 6, the greatest distance they can get from each other is 90 degrees. And it looks, we call it octahedral. 1, 2, 3, 4, 5, 6. I know it sounds strange with 6 to be called octa, but there you go. Because it's an octahedral shape. And so these bond angles are all identical. They're all 90 degrees. So those are the basic shapes. Now, these are what we call the groups. These are the group shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. That does not mean that the molecules themselves are that shape, because when we talk about the shape of the molecule itself, we basically leave out the lone pairs. Like, for instance, water, we say is bent. But the group that it's in is tetrahedral because it has two lone pairs. So it has 1, 2, 3, 4 electron groups. That is the tetrahedral group. But since we don't really see the electrons when we're looking at a water molecule, we just see the atoms. If you're just looking at the atoms, it looks bent. Okay, well, I'll talk more about that in a second. So this is how we use basic rules to figure out which group we're going to be in. So as I mentioned before, the group arrangement is defined by both bonding electrons, single, double, triple, and non-bonding electron groups, or lone pairs. We count both. So then the shape of the molecule is just the three-dimensional arrangement of those nuclei of the atoms joined by these groups. And the shape is classified using this formula. And we're going to be coming back to this formula over and over and over again, the AX formula, where A is the central atom. So they're all going to have a central atom. It's got to have a central atom or it's not a molecule. X are atoms surrounding the central atom. And we just use the designation X for atom. I don't know why, because you can't use A again. So X are the number of surrounding atoms. They would be like 1 or 2 or 3 or 4 or 5, however many. And then E are just electrons, lone pair electrons. And there can be 0, 1, 2, 3, however many. And then we basically look at the structure we've made. For instance, I just mentioned water. Let's look at water again. So let's draw water again. So here's my water. It's got 1, 2, 3, 4. So there's my structure of water. So if I want to know what group, what shape this is going to be, what group it goes into, I look at my central atom. Oxygen is my central atom. Okay. So central atom is oxygen. X is how many atoms are surrounding it. So how many atoms are surrounding water?
2.
2.
2 hydrogens.
Yep. And then E is the number of lone pairs surrounding now remember, the lone pairs are only on the central atom. Because if there's like, oxygens or halogens or whatever surrounding the central atom, there's going to be a butt ton of lone pairs. But this is only on the central atom. So how many pairs of lone pairs do we have around the central atom?
2.
2. So we said that is AX2E2. And so we add these two together to figure out which overall group we're in, which would be AX4. That's tetrahedral. So the overall shape of the molecule is going to be tetrahedral. It's going to be in that tetrahedral group. The actual shape of the molecule will be defined by these two numbers. How many are atoms? How many are electrons? And so then we go to our table. So here's our table. Yikes. And we look at the table and we see, okay, 4. It's got 4 tetrahedral. It's not AX4. It's not AX3E. It's AX2E2. Oh, that means V-shaped or bent. And so we say, okay, that means water is a bent molecule. So again, you don't have to memorize the shapes. What you do have to know is which group is this going to be in, depending on how many electron groups are around it, and then be able to identify how many atoms and how many electrons are there. And that will tell you the precise molecular shape, not just the group that it's in, but what's the precise shape of that molecule, just looking at the atoms. So let's look at the bond angles a little more closely. So the bond angle is just the angle formed by these three nuclei. 1, 2, 3. So if this is BH3, this angle is the angle of the hydrogen, boron, hydrogen. What's that angle basically between the two hydrogens? And in an ideal world, with this particular shape, it would be 120 degrees, because that gives you the maximum distance of the hydrogens away from each other. And we call those ideal. Those are the ideal bond angles. Like if everything is perfectly symmetrical, linear is 180. The trigonal planar is 120, and tetrahedral is 109.5. When everything is perfectly symmetrical. Now, that's obviously not going to be the case as it was in the water example. It isn't completely symmetrical all the way around. Because for instance, we look here on the bottom, if there's a double bond between the central atom and one of the other atoms, remember what I said, that's twice as much electron density as a single bond. So there's going to be more electrons there than here or here. There's going to be more electrons there. And the more electrons there are, the more it will repel these two atoms and will push them down a little bit. And so this angle will now be slightly greater than 120 degrees. And this angle in here will be slightly less, because it'll push those two X atoms, it'll push them a little bit closer together. Also, if we have a different atom, like if we have something like chlorine or fluorine or iodine, something with a lot of electrons on it, that also is going to push these two a little bit closer together. So if this is like iodine or something, and it's like 53 electrons, that's pretty dense. That will also push the other two atoms a little further away. And lone pairs actually push those other groups further away. And it may seem like weird at first, but when you think about it, this lone pair of electrons, they don't have any nuclei attached to them. And remember, the nuclei are positively charged. So there's no positive charge here, just two negative charges sort of, floating in space. That is going to repel these other two atoms away from it. It's basically like an uncapped pair of electrons with no positive charge to sort of knock it down a little bit. So that is more charged than just a bonded pair of electrons that has a nuclei on either side. This is just two electrons without anybody. So it pushes atoms a little further away. And so this also increases this angle and decreases the angle between the two atoms, like we see in water. That's the situation in water, where since we have two lone pairs here, this angle between the two hydrogens is a lot less than 109 degrees. I think it's like 104 or something like that. They're pushed together because there's two lone pairs repelling them even more. So I won't ask you to know precisely what those bond angles are, because that's not important. What you will need to know is that it's going to be more than the ideal angle, or is it going to be less than the ideal angle? And by knowing what the densities of the electrons are, whether it's a double or a triple bond, or knowing that a lone pair repels atoms more than just a regular bond, you'll be able to predict whether or not that bond angle is more or whether it's less, okay? So here's just some examples. We'll just go through a couple of examples. Linear shape. The classic example for a linear shape is carbon dioxide. And why is that a classic one? Well, because, whoops, let me go back. Because we have carbon in the middle, oxygen on that side, oxygen on this side. So basically, surrounding the central carbon are two regions of electron density. This double bond here, and this double bond here, two. So that makes carbon dioxide linear. So if we look at the shape, this oxygen and this oxygen are basically as far apart from each other as they can possibly get. And that is a line. So carbon dioxide is a linear molecule. Okay? We're going to do lots of examples of these. So here's some examples of the trigonal planar. And you'll see a lot of these with carbon with a double bond and two singles. That makes for three regions, something like this. So here, carbon has three regions of electron density around it. One is the double bond, and one is the single bond to the hydrogen, and the other is a single bond to a hydrogen. Three regions of electron density around the carbon. No lone pairs, so only three. So that will be planar, trigonal planar. What do you think this bond angle will be between the two hydrogens? Will it be greater than 120 degrees or less than 120 degrees? What's your prediction?
Would it be greater since the double bond is like pushing? Never mind, I don't know.
It is pushing. It's the double bond is a greater density of electrons, and so it is pushing those two hydrogens away from it.
Oh.
So where the hydrogens would be here, they're now sort of pushed away from the oxygen a little bit more. So what does that do to this bond angle, this hydrogen, carbon, hydrogen angle? Does it make it greater than 100? Does it open up and become greater than 120 degrees, or does it close down a little bit and become less? What do you think? They're pushed closer together slightly. So when they're pushed slightly closer together, does that increase the angle or does it decrease the angle?
Decrease. So
decreases. Right, it gets smaller. The distance between those two hydrogens becomes slightly less because they're both being pushed away from the oxygen, double bond. So they're being pushed slightly closer together. So this angle in an ideal world is 120 degrees. Now it's a little bit less because it's been pushed slightly closer together. So the bond angle is less than 120 degrees. That's right. And so these are some of the factors, as I've mentioned. Non-bonding lone pairs. They repel other groups more, as I mentioned, because there's no cap on them. There's no positive charges here. And so it's nothing but negative charge. And so it's more repulsive than, say, a bonding region would be with 2 electrons in it, but with nuclei at the end. So it basically brings down that repulsive charge a little bit. So this pushes things much closer together. And here you can see that with tin dichloride, this goes from 120 or 120 degrees we would expect, all the way down to 95. That's a big difference. So just having that lone pair there really pushes those two closer together. Oh, and here's the molecule I just showed you. You can see that it would be 120 degrees, but it was lowered to 116 because those hydrogens are pushed slightly closer together because there's more electron density in a double bond than there is in a single bond. So those are basically two things that affect bond angles. For some reason.
For the first one, is it because of chlorine attracting each other that it also decreases, or is it just the lone pair?
The chlorines won't, they don't attract each other, but they have more electrons. So chlorine, remember, was going to look like this. Oops, let me go back. Yeah. So our 2 chlorines are going to, damn it. There we go. So our 2 chlorines are going to look like this. They have a lot of lone pairs of electrons. And so there's already a lot of electron density here. And so if I put even more electron density up there, it's going to push them even further. Hydrogen has very little electron density. So if I have, just think about how, when we looked at how ionic bonding is formed, we looked at the 2 charges and the distance between them. And so if I get much bigger charges, like I do on chlorine, if I have a lot more electrons in a region, it's going to repel even more. And so these two push each other apart more than just hydrogens would.
How do we state the angle? Do we state HC double bond O 122 degrees, like that? If it's asked the angle.
Yeah, it will be the HCO bond. You just write HCO bond, and then the HCH bond.
Oh, okay.
You don't have to include like how many bonds there are, but that's the angle, the HCO bond angle. Okay. Yeah. Why I have 2 of them exactly, 2 slides exactly like each other, I do not know. Anyway, so here's some more advanced shapes. So these are the tetrahedral shapes, the four groups, and there's 3 basic shapes we'll get. So the classic tetrahedral shape you will see when you have complete symmetry. And so you'll see something like, CH4 methane. So it's completely symmetrical all the way around. Or silicon tetrachloride, or anything that basically gives you the same structure all the way around. Now, you get something called a trigonal pyramidal shape when you still have the tetrahedral group, but you've lost one of the atoms and replaced it with a lone pair. And you'll see that, like the classic example of this is ammonia. So it's got the lone pair on the top, and then 1, 2, 3 hydrogens surrounding it. And so this lone pair actually pushes those 3 hydrogens slightly closer together so that these bond angles are now a little bit less than 109.5 because that lone pair repels them slightly. And then the classic example of this group where you have 2 lone pairs and 2 atoms, of course, is water, as I've mentioned. And then there's some other ones, but the classic example is water. We say it's bent because if you just looked at the molecule without the lone pairs, it looks like it's bent. When you add the electrons, then it makes more sense that, oh, that's why it's that shape, because there are 4 regions of electron density around the oxygen, and it makes it this particular shape. So these are the groups with 5. We won't do too much with like 5 and 6, but these are the things you should be aware of. So these are also in the table, so you don't have to memorize these. But AX5. So if you have 5 atoms, which are basically identical, surrounding the central atom, you'll get the classic trigonal pyramidal shape. If there is a lone pair in there, you get this AX4E. We call that a seesaw shape because it kind of looks like 1, 2, and then 3, 4. So it kind of looks like a seesaw. Yes.
I still don't get why the angles in trigonal bipyramidal are different. One is 90 degrees, one is 120.
Right. Yeah, because the way they arrange themselves is basically you have straight up and down. So that's as far apart as they can get from each other. And then you have 3 surrounding in the middle. So 1, 2, 3. And that's the most stable way to have 5 atoms to minimize the repulsions between them, is to put them in that shape.
Okay.
Because anytime you move one, it's going to get closer. Like if we move this one a little bit, then it gets closer to this. If we move any ones in the middle, they get closer to each other. That's the lowest energy, most stable way to keep those 5 atoms from repelling each other, is that particular shape. And so we call these axial positions on the top and the bottom, because they're sort of like an axis, like of the Earth axis. And we call these 3, just like the sort of Earth, we call these equatorial positions. And I'll talk more about that in a second. So here we have, so this is the seesaw when there's 1 lone pair. When there's 2 lone pairs, like we have here, we have a T shape, where it looks like you have an atom on the top, on the bottom, and the one pointing straight out at a 90-degree angle. So that would look weird by itself, but remember, it's the lone pairs that are forcing this conformation. So it basically looks like this. So that's strange that you wouldn't think that 3 atoms would organize themselves that way, but they wouldn't unless there was the 2 lone pairs forcing them into that configuration. And then finally, if we have 3 lone pairs, you get linear shape again, because that gives us the greatest distance between the 2 atoms, and the greatest distance between the atoms and the lone pairs is in this particular conformation. And since the lone pairs are more repulsive than the atoms, we put those in the equatorial positions around, because that gives us 120 degrees separating them rather than the 90 degrees separating them. So generally, lone pairs go in the equatorial region to give them the greatest separation from each other. And I'll show you that right now. And don't worry, we're going to go through all this again on Thursday. So with the 5 electron groups, as I mentioned, generally we put our atoms in the axial positions, and we put the lone pairs in these equatorial positions, because the equatorial positions get to be further apart from each other. So these repulsions are weaker because they're further apart than these repulsions because they're closer together. There's only a 90-degree angle between axial and equatorial, there's a 120-degree difference between the three equatorial groups, okay? Let me clear that. So you get more separation there. And then finally, when you have 6 surrounding, these are the octahedral groups. And so when you have AX6, there's no lone pairs. You get the perfect octahedral shape. So sulfur hexafluoride, the 6 fluorines surround the sulfur and space themselves as far away from each other as they can. When you introduce a lone pair, you get this odd shape. You sort of get this square pyramid shape, basically sitting on a lone pair of electrons. When you introduce 2 lone pairs, you also get a square, but with a lone pair on the top and a lone pair on the bottom. So again, don't have to memorize any of this. It's all in the tables. Just remember what contributes to the increase or decrease from the ideal bond angles. And the ideal bond angles will also be in the table, so you don't have to memorize those as well. But you will see 109.5 over and over and over again.
Is
Yes.
binary molecules 0 degree or 180?
Oh, they're not considered. We don't consider those there because they're all linear
Okay.
by definition. They're just because there's just two molecules bound to each other. That's it. So they're all linear molecules.
Okay.
Right. So remember that. So for the first 2 periods, we can't have more than 4 regions. It's basically impossible because remember each region is at least 2 electrons, and they can't have more than an octet. It's only when we get to periods 3 and above that we start to see 5 and 6 regions of electron density, get these like really weird shaped molecules. All right, so that is about it. That's sort of a general introduction. Let's go to the recitation and look at some of the questions and see if we can answer them. New share. Let's do a whiteboard. So the very first question is about my favorite molecule. And shows you how exciting my life is. I was watching some of these videos to see if they would work for the class. And one of them was Crash Course. Has anyone seen any of the Crash Course videos? They're pretty good. I like Crash Course and Professor Dave the best, but Crash Course is really good. And they also mentioned that water is the most important molecule on Earth, just like I've been telling you the whole term. So now you know it's true. So the first question is basically, let's draw the Lewis structure of water. Well, that should be pretty easy. Who goes in the middle? We've done this plenty of times. Who goes in the middle in a water molecule?
Oxygen.
It's got to be oxygen. It's not the least electronegative element though. So why does it go in the middle?
It forms 2 bonds instead of 1.
Hydrogen can only form 1 bond. Oxygen can form more. So oxygen has to go in the middle. And so those are our 2 bonds. Oxygen has 6 valence electrons. Hydrogen has 1 each, so a total of 2. So we should have 8 electrons in our Lewis structure. Here's 2 bonds. Each one of them has 2 electrons in it. That's 4. So we have 4 electrons left over. Leftover electrons always go in the middle. And here is our 4 electrons going on oxygen. All right. So what is the overall, what's the geometric group of this particular structure? Now remember, we're going to go for A, X, E. So A is oxygen, our central atom. How many atoms are surrounding it?
2.
Mm-hmm. And how many lone pairs are surrounding it?
2.
2. So we look up in our chart which group that is. Now we should probably already know 1, 2, and 3 fairly. Even I have trouble remembering 4 and 5 and 6, but 1, 2, and 3 I kind of remember. 2 is linear, 3 is trigonal planar, and 4 is tetrahedral. After that, things got a little foggy. So we add these two together, we see that we have 4 regions. So it's going to be, so the group, so the question says, what is the geometry of this molecule? It means what geometric group does it fit in? And the geometric group that it fits in is tetrahedral. Now that doesn't mean that the molecule is tetrahedral, but the group that it's in, because there's 4 electron groups around it, the geometric grouping of that situation is a tetrahedral. So the answer to 1B would be tetrahedral. Now, if we're going to draw the Vesper structure, the way we sort of draw these things is we have straight lines for molecules or electron pairs that are in plane. Basically, if we look at a flat plane, we have straight lines for things that are in that flat plane. We have these sort of dashed lines for things that go behind the plane, and we have this wedge for things that come out. So with the tetrahedral shape, we have 2 straight lines, one going into the plane and one coming into the plane and one coming out. Ooh, out. So in this way, we could draw a number of ways. So we can put our hydrogens in one plane and have one lone pair going behind the plane and one lone pair going in front, or any sort of, we can do that in any way we want. But that's basically how to represent 3 dimensions with a tetrahedral shape. We have, like for instance, if I have methane, I draw methane like this. Other way. So that tells me that one hydrogen is coming out at me, one hydrogen is going back, and the other 2 hydrogens are in plane. That's really the only things you have to, when you're drawing these structures, that's really the only thing you have to do. If the atom is behind the plane, you get a hatched line. If it's coming out of the plane, it's a wedge, and if it's in the plane, you just use a straight line. That's all you have. You don't have to draw balloons or anything like that. Okay. So that would be the shape. This would be like the Vesper model here. And usually when you draw water, you can draw it in any way you like, as long as like 2 things are in the plane, one is going in, one is coming out. So what is the bond angle? That's the next question. So there's only one bond angle in water, when you think about it, because we don't look at the bond angles of lone pairs because they're not bonded. So the only bond angle there is this one. the HOH bond angle. So what is it? So what in an ideal situation with a tetrahedral molecule, what's the ideal bond angle?
109.5.
Good old 109.5. In methane, all those hydrogen-carbon-hydrogen bonds are all exactly 109.5 degrees. We've measured them experimentally, and that's what they are. But with water, it's either going to be 109 degrees, it's going to be greater than 109 degrees, or it's going to be less than 109 degrees. Which one? Whoops. Put that in the wrong place. So which is it? Is it precisely 109? Is it greater than 109? Or is it less than 109?
Would it be less than because the pairs are pushing down?
Exactly. Very good. Yeah, it's less. I forget what it is precisely, but yeah, we've got these two lone pairs there. And so it's going to repel these two, it's going to repel this electron region and this electron region away from them. And so this angle is now going to be less than 109. I think it's like 104 or something like that. I can't remember exactly. I should, because water's so damn important. Yeah, so the angle would be less than 109. And then the final question, this is something we'll be dealing with on Thursday, is the polarity of the molecule. So let's draw it yet again. Now, polarity results from an uneven distribution of electrons. That's all polarity means. It means that you don't have an even distribution of electrons along the molecule. And so first we'll talk about whether or not a bond is polar, and then whether or not the molecule is polar. So first, it says place partial positive and negative charges on the hydrogen and oxygen atoms based on their relative electronegativities. Well, the oxygen is electronegativity, I think, of 3.5, and hydrogen is 2.1. So that is a big difference in electronegativity. And we're going to learn that if the electronegativity difference, or delta En, is more than 0.4, that makes it polar. And in fact, if it gets more than, I think, around 1.8, it becomes ionic. Because basically it becomes so polar that the electrons, instead of being unequally shared, just not shared at all. They're just being pulled apart. So we have, we have a difference of 1.4 here, difference in electronegativity. So is that going to be a polar bond or a non-polar bond?
Polar.
It's going to be polar. It's a lot more than 0.4 difference. And so we're going to learn there's a couple of different ways to represent that. So what does that mean that it's polar? Well, remember what I said this morning, that each of these bonds is nothing more than just the density of electrons between them. That's all it is. Just a little cloud density of electrons located between those two atoms. Now, because oxygen has an electronegativity of 3.5, remember what electronegativity means. It means it's pulling. It's able to pull on that cloud a lot more than hydrogen can. And so this density, instead of looking relatively even, starts to pile up a little bit more closer to the oxygen and a little bit less around the hydrogen. And so we see that density now becomes less around the hydrogen than it was, and more around the oxygen, which means the oxygen becomes slightly negatively charged. We say it as a partial negative charge. Why? Because it has more density of electrons around it than an oxygen atom by itself. It has higher density than an oxygen atom by itself. The hydrogens have a lower electron density around them than hydrogen atom does by itself. And so it has a partial, and we use the delta sign for slight or a small increase. It has a small positive charge. So we have a partial negative charge, not a full negative charge. This isn't an ion. That's a full ion. That is a charge. That oxygen has 8 electrons around it, 2 more than its normal valence of 6. This oxygen has a greater electron density around it than just 6 electrons. It's got these two, and it's got slightly more of this pair, which is 2, and slightly more of that pair, which is 2. How much more? More. It says more than that. And so we say it's a slightly, partially negative charge. That makes it a polar bond. And the other way we represent it, with the small delta positive and delta negative, the other way we represent that is with a line. We draw a line like this. And we point towards the more negatively charged atom. So this arrow points toward the area of higher electron density. And that means that this looks like a positive, right? Looks like we have a little positive sign. That points towards the partial positive. So if you ever wonder what direction it's in, look at the back end of the arrow and it tells you, oh, that's a positive sign. It should be pointed toward the more positive. And so what we have is a line that goes like this. That bond is polar. This bond is polar as well, both pointing towards the oxygen. So because of that, the last question is water a polar compound? Now, based on this picture, what do you think?
Yes.
It is. Who's taken physics?
I.
Who can tell me what a vector is?
Vector is a magnet quantity that has a magnitude and a direction.
Yeah, exactly. It's a number that's associated with a direction, and that's what these are. These are vectors, because there's a quantity. We don't know exactly what the quantity is. It's just saying if there's more of one thing and less of another thing. So there's a quantity. It's not a precise quantity, but it's a quantity, and it's pointing in a particular direction. And so if we look at these two vectors, notice they're both pointing up. And so since they're both pointing up, the net, if we add them together, would look like this. Pointing up and towards the oxygen and towards the 2 lone pairs. That makes it polar. We call this a dipole. We call each bond a dipole. A dipole just means two poles. One is a partial positive pole. The other is a partial negative pole. 2 dipole. So those 2 bonds are both dipoles. Now, just because a molecule has a dipole doesn't mean it's polar. I will give you an example. And so one of my favorite examples is carbon dioxide again. So here's our old friend carbon dioxide. Now, as I mentioned, oxygen has an electronegativity of 3.5, and carbon, I believe, is 2.1. No, 2.5. Anyway, it's somewhere around 2.5. I should have my table in front of me as well. Anyway, but the difference in electronegativity is greater than 0.4. It's a lot more than that. So is this bond, these carbon-oxygen bonds, are they polar or non-polar? It has a greater electronegativity difference than 0.4.
You mean the
Polar?
They would be polar, right. This carbon-oxygen bond would be polar because the oxygen has a much higher electronegativity than the carbon does. It's like 2.5 maybe. That's a much bigger difference than 0.4. It's a big difference. That means it's a polar bond. And so if I was to draw my representation, carbon would be slightly positive, and both these oxygens would be slightly negative. Because the density of electrons is going to be higher around the oxygens than it is around the carbon. And as we found out this morning, the oxidation numbers of the two carbons are both -2, and this carbon is +4. That also indicates that it's probably, those are two pretty polar bonds. So I have two polar bonds in a molecule, but let's look and see where they are. There's my partial positive, there's my partial negative. So when I draw my indications of the dipole, they're going to look like this. So this bond is polar, this carbon-oxygen bond is polar, pointing in this direction. This second carbon-oxygen bond is also polar, pointing in the opposite direction. So basically what I have is two vectors that are exactly the same size, pointing in exactly opposite directions. So when I add those two together, what do I get?
0.
I get 0. Because basically they cancel each other out. So if I have a dipole in this direction and a dipole in that direction, and they're both identical, and they're both pointing at exactly 180 degrees apart from each other, when I add them together, I basically get a plus and a minus. I add them together and I get nothing. So this molecule has two polar bonds, but the molecule itself is nonpolar. And that's why these shapes are so important, because it's fairly easy to understand like whether a bond is polar. You know, if the two atoms have a high difference in electronegativity, that's polar. If they have a small difference in electronegativity, well, that's nonpolar. But it's not as simple as that, because you have to consider how they're arranged in space. And so we have two examples. Water has two polar bonds, polar. Carbon dioxide has two polar bonds, nonpolar. Why? Because they're different shapes. Okay? So let's do number, well, actually, you guys have a look. Which one would you like to do next? You want to just do the second one, do nitrate? Or does anyone have any questions so far? That's probably be a good time to ask if you have questions. We've covered a lot today as well.
I think I'm kind of confused on the Vesper shape with the
Okay.
wedges and everything. So could we look at number 2?
Yeah, let's just do another one then. Yeah,
Thanks.
let's just do another one. So we have nitrate. Or nitrite, I guess, nitrite, ion. So first we got to draw the Lewis structure. That's always the first thing to do, because you can't draw the three-dimensional structure until you know the Lewis structure first. So who's going in the middle?
Nitrogen?
Nitrogen, for a number of reasons. A, there's one of them. Generally, if there's a single atom, it usually goes in the middle. Again, that's sort of for symmetric purposes. 2, it has a lower electronegativity than oxygen. So that's the other reason it's going in the middle. So let's do that. So here's our nitrogen, and then oxygen here, oxygen there, couple of bonds. All right, so how do we figure out how many total electrons should be in this structure?
Each oxygen has 6 and nitrogen has 5.
Yep, exactly. So we have 6 and 5 and 6. So that equals 17. So are we done?
And then you gotta account for the ion.
There you go. 18. So 18 electrons. So we start by decorating the outside and making sure they have a full octet. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That gives both oxygens a total of 8. So they're happy. That's 12. I have 6 left. Oh, 6 left. And how many have we put in bonds? I almost forgot. How many have we put into bonds?
4 electrons.
Yeah, 4. So we got 1, 2, 3, 4. So now we're down to 2. So there's 2 electrons left over. And if any electrons left over after filling all the octets on the outside, you put them in the middle. So there we go. Now, that's the first stage. Second stage is figuring out, does everyone have a full octet? Well, we know that the oxygens do because we gave them a full octet. The question is, does the hydrogen? So does the hydrogen have a full octet of electrons?
No.
Couldn't hear you. What?
No.
No. How many electrons does it have total?
1, 2, 3, 4, 5, 6, 6.
Yeah, it has 6 total. We're not dealing with valence electrons yet. We're dealing with total electrons. So it's got a lone pair, 2. It has 2 bonds, 2 electrons in one, 2 electrons in the other, for a total of 6. So it only has 6. So what are we going to do to make sure it has 8? How are we going to get 8 electrons to the nitrogen?
Transfer a lone pair from the oxygen.
There you go. Yeah, let's just move these. Make another bond. So oxygen will share another pair of electrons with the nitrogen. So now, how many total electrons does nitrogen have?
8.
Now it has 8. So it's got 3 bonds,
8.
6 electrons in bonds, and it's got a lone pair. And that's generally what nitrogen's going to look like. The more of these you make, you're going to notice that nitrogen pretty much 80, 90% of the time has 3 bonds on a lone pair. That's generally what it does. So we've counted all the valence electrons. We figured out how we get 8 on everybody, total electrons on everybody. Now we need to figure out the charges. So what is the number of valence electrons? So we have oxygen A and oxygen B. How many valence electrons should oxygen have? Like oxygen in general, how many does it have?
6.
It should have 6, right. How many does oxygen A actually have? Now we're just looking at valence electrons, not total. And remember, the valence electrons are the mine electrons.
1, 2, 3, 4, 5, 6.
It has
6.
6. So it's got these 2 lone pairs, 1, 2, and half of the bonds, half of the electrons from bonds. So we just cut the bonds in half, and so it has 2, 4, 6. So that oxygen has no charge on it. And you'll see that over and over again, oxygens that have 2 bonds and 2 lone pairs have no charge. That's what oxygen normally does. It has 2 lone pairs and 2 bonds. Now the nitrogen, how many valence electrons should nitrogen have?
5.
Should have 5. How many does this nitrogen have?
5.
It does. Yeah, there's 3 bonds. It gets to keep 1 electron from each one for 3, and it has a lone pair for 2 more. So it's got 5. So there's no charge on the nitrogen either. So far, so good. Now, let's look at oxygen B. We know that oxygen should have 6 valence electrons, as we mentioned before. How many does this one have?
7.
It has 7. So it has a charge of -1. Now, we learned this morning, just this morning, that there's more than one way to draw this particular structure, right? What's the other way we could have drawn this structure?
Let oxygen A become like oxygen B.
Yeah, oxygen A could have had the negative charge on it, and oxygen B could have the double bond. And so we also learned that those two are in resonance. And if we were to draw a hybrid resonance structure, it would look like this. An average of the two would look like this. And this isn't really essential. You can answer the question without doing this. I just sort of wanted to remake the point. So here's our nitrogen, our 2 oxygens, and remember, it looks something like this. Where these electrons are delocalized. And so it kind of looks like this. Now, this isn't essential for answering the question. You can answer the question with the negative charge there. That's fine. So, what is the geometry of this particular ion? What group does it fall into? When we do A, X, E, what do we get from this particular setup? So nitrogen is our central atom. How many atoms are around it?
2.
2. It's got 2 oxygens around it, right? And how many lone pairs does it have associated with it?
1.
1. So it's AX2E1. So we looked that up. AX2E1. Which group is that going to be in? How many electron groups are around the nitrogen? How many regions of electron density? That's the other way of putting it. Other than electron groups, how many regions of electron density are there around the central nitrogen? And how many places around the nitrogen are we going to find electrons? The answer is either 2, 3, 4, 5, or 6.
Wait, is bonding group the same thing as a region?
Yep.
Okay, so then
Yep.
2.
2 bonding regions plus.
Plus
There's another place you're going to find electrons around the nitrogen.
that lone pair.
That lone pair. Right. So when you think about how many regions of electron density or how many electron groups, that means the same thing. How many are around the nitrogen? There's 1 there, 2 there, and 3. Those are the 3 places where I'll find electron density. So there's electron density there, there's electron density there, and there's electron density up there. 3 places where I'll find electron density. So if there's 3 places, 3 regions around nitrogen, what general shape is that? What group is that in? With 3 groups of electrons around a central atom.
A trigonal planar.
Trigonal planar. Yeah, looks like the triangle. That's the greatest distance that 3 things can be from each other. is in that triangle shape in a plane. So 1, 2, 3. And we know the angles are all going to be 120 degrees. That's like of an ideal triangle, got 120 degrees. So what we have is nitrogen, these two oxygens, and our lone pair. So if I was to draw the shape of it, so I say it's in the trigonal planar group, but that's not the shape of the molecule. That's different. It's in this group. But remember, the shape of the molecule only considers the atoms, just the atoms. And since it's AX2E1, what shape is that?
Oh, it's bent.
It's bent. And so I leave out the lone pair, and I just leave it like that. It's bent. And so I would just reply, it's bent. And the fact that I have these two straight lines means they're in the plane. I would not draw it like this. Because I don't have an oxygen going out and an oxygen coming in. I mean, you could draw it like that, but it's, if you want to make the point that they're in a plane that's planar, you just draw the simple straight lines and leave it at that. So this is a bent molecule. So my question to you would be, what is this bond angle? Is it greater than 120? Is it less than 120? Or is it 120 degrees? So the ideal angle would be 120 degrees. What is it? Is it more, less, or 120?
Less, because the nitrogen's pulling away.
It is less, right? Why is that?
Lone pair.
Exactly. When we're drawing just the stick figure, when we're drawing the Vesper stick figure model, we don't include the lone pairs. We're just looking at the shape of the molecule. But that lone pair is there, and so that pushes those two oxygens away from the top, and that's why it's, this angle is slightly less. I don't know how much slightly. I don't know what it is precisely. It's less than 120 degrees. Yeah, again, you do not need to know. You need to look it up if you want, but you just need to know whether it's more or whether it's less and why. That's the key. So that pretty much answers. Oh, let's put partial positive and negative charges on the nitrogen and oxygen. Let's do that. So we'll determine whether or not it's polar. So there's my nitrogen, there's my oxygen, there's my lone pair. I'm not going to bother putting the other, I just want to put the dipoles in. So nitrogen, I believe, has an electronegativity of 3, and I think oxygen's is 3.5. So the difference in electronegativity is around 0.5. So is that going to be polar or non-polar?
Barely polar.
Very polar?
Barely polar.
Barely polar. You're right. That's very good. That's exactly right. Because the cutoff for polarity is around 0.4. So we do have two polar bonds, but not particularly polar. So here's what the two are dipoles. Let me change the color up. the two dipoles would be running along these lines because that's where the bonds are. Now, which end gets the arrow? Is the arrow going to be pointing toward the nitrogen or pointing toward the oxygen?
Towards the oxygen?
Right, the oxygen is more electronegative. So they're both going to be pointing toward the oxygen. And then, so my plus goes there. So that means that my oxygens are going to be slightly, and I mean very slightly, more electronegative and slightly more charged. But also remember that there's an extra electron floating around here. And so this dipole difference would be a little more than normal because there is an extra electron, there is an extra charge. If it was not charged, that dipole would not be as big, but it's slightly bigger because there's an extra electron that's delocalized in here. And the oxygen gets to keep that more than the nitrogen does. So we would put a slightly positive on the nitrogen. And so we have two polar bonds. Is this a polar molecule?
Yes.
Yes, because these two bond dipoles are both pointing away from the nitrogen. They do not cancel each other out. And so what our net dipole would look like, and we'll deal a lot more with this on Thursday, our net dipole would be like that, pointing away from the nitrogen and towards the oxygen. So this would be a polar molecule. The fact that it's charged also kind of gives it away that it's going to be a polar molecule. An ion, sort of basically by definition, is going to be a polar molecule because it has a charge in it, unless it's completely shared completely equally by like all the atoms. And that's fairly rare that you would have a non-polar charged species.
How do you indicate that it's charged in the VS-EPR drawing?
No, I don't think so. I don't think that's necessary because that negative charge is distributed between the two oxygens. Neither one of them has a charge on it. So, but this delta negative and this delta negative is going to be slightly bigger than would be otherwise. And so that would be indicated by the size of these dipoles. That would make them a little bit bigger. But remember, they're still not negative. They're still not completely negatively charged because basically these two oxygens are sharing the extra charge. So their charge would be more, but it still wouldn't be a full charge. And that's something we're actually going to be doing in our lab on Thursday, is looking how charge is distributed in these polar molecules. Because sometimes you can have something like nitrogen trifluoride, for instance, where those fluorines are so electronegative and they're all pulling on electrons from nitrogen, that basically the nitrogen takes on more than one charge because those three fluorines are pulling on it so much. So we'll be able to see that in our lab on Thursday, exactly how when the arrangement of atoms contributes to partial charges. But in this instance, because we have a total of -1, like one whole charge, neither of those oxygens will have a full charge. Hey, buddy. I don't think. Okay. So look through. Who's got the next question? Or who wants to? Here's my buddy. How you doing, Jerome? Did you get any ice cream? No?
Professor,
Yes.
I just needed help finding something on Canvas, like for the electric negativity. Is there a chart on there besides the Vesper one? Like
I
that tells.
don't. No, I don't think I have included an electronegative. I will. I
Okay.
will. I will do that.
Okay, thank you.
I'll just put a simple electronegative chart. That's a good idea. Because yeah, I gave the link to P table, the periodic table. You can go there, and like each click gives you like all the information you want, and you can print one from there. But what I'll do is I'll just there's like a really simple table that just has the electronegativities on it. That's really helpful for this sort of thing. So I will put that. I'll put that there. That's a great idea. In fact, I meant to do that earlier, and I just left my mind.
Can we do the Vesper for 3A, please?
For 3E,
A.
A, SF6, sure. All right, buddy, I'm gonna need my seat back, okay? Be right with you. So SF6, let's gonna be a lot of electrons in this one. So total electrons, how many does sulfur have? Valence electrons. Excuse me.
6.
6. So sulfur's going to have 6. Fluorine has how many?
7.
7. And there's 6 of them. Good Lord. 42. There's 48 electrons. Man, I'm going to be tired just making dots. So 48 electrons. So let's put our sulfur in the middle and put 1, 2, 3, 4, 5, 6 fluorines around it. 1, 2, 3, 4, 5, 6. So we have 6 bonds, and that's how many electrons?
Uh, 12.
12. So I got 30 electrons to go. Now remember, first thing you do, decorate the outside to make sure everybody gets an octet. And so each fluorine has 2 from the bonds, and so we give them all 6 to fill their octets. And because that's, oh, wait a minute.
Wait, don't you subtract the 12 from the 48?
Oh, 48, duh. Right, I'd already done that. Right, so we should have, that's good because I was going to run out of electrons. So 48 minus 12 is 36. Thank you, because I would have looked really dumb. So 36 electrons left to go. So 1, 2, 3, 4, 5, 6. So we have 6 fluorines, and they each get 6 electrons. That means we're done. That's all of them. So I have distributed all the electrons. So this is my Lewis structure. Let's figure out who needs electrons. So we know that fluorine doesn't need any more electrons because we made sure each of them got 8. So they have 3 lone pairs and a bond for a total of 8. So all the fluorines are good. And you'll notice when you're doing these, fluorines always have 3 lone pairs and a bond. Always, always, always. They never have anything else unless they're an ion, and then they have 4 lone pairs. But fluorine always makes 3 lone pairs and a bond. Fluorine doesn't make double bonds. You can't get it to share electrons in any other way because it's so electronegative. It's not giving up any of those lone pairs under any circumstances. So always going to have 3 lone pairs and a bond, fluorine is. So those fluorines are fine. What about the sulfur? How many total electrons does sulfur have?
12.
That's 12. Is that okay?
Yeah, so the third period.
That's right. So sulfur routinely, I keep telling everyone, Sulfur and phosphorus, those are the two things to look for that routinely violate the octet rule. I think they violate it more than they follow it, really, particularly in complex structures like this. So sulfur's fine. It has more than enough electrons. All the fluorine has enough electrons. So we're done. So the question is, what shape is this? So AX, oops. So we go back to good old AXE. So A is our central atom, that's sulfur. How many electrons are around it? How many electrons, oh, sorry, how many atoms surround the central sulfur?
6.
6. So we have AX6. And then how many lone pairs does sulfur have?
None.
None. So basically we just have AX6. And if you look up AX6, that's octahedral. That's an octahedral. Both an octahedral. It's both in the octahedral group and an octahedral shape on top of that. And so if we were to look at what that would look like, octahedral. Now again, I am one of the worst artists ever. All my art school friends made fun of me as an undergraduate. Yeah, I couldn't draw a stick figure. But here we go. So I've got my sulfur in the middle. And so I've got basically 4 atoms around the middle. So 1, 2, 3, 4. I've got 2 coming out and 2 going back. And then I have 2 in the axial position, 1 here and 1 there. So that's basically how you would draw an octahedral structure. So you have this sort of square surrounding the sulfur. Remember, these are the equatorial positions, and these are the axial positions. Although it's not as important than with the group of 5, because all these angles are 90 degrees. They're all the same. So it doesn't really matter how you put it together. It makes a much bigger difference when you have like a lone pair or something in there to put them in the equatorial. So generally, if you're wondering which ones to put in the equatorial and which in the axial, generally if you have like 4 atoms that are the same, they would go in the equatorial, and 2 atoms they're different, they would be in the axial, just again to preserve symmetry. So, do we have dipoles in this structure? Do we have bond dipoles? I'll put it that way. Are there bond dipoles?
What's the electronegativity of S?
Sulfur is around 3.3 or so. It's a little less than oxygen. I think it's around 3.
So yes.
And fluorine is 4. So all of those bonds are going to be polar, every single one of them. And they're all going to be pointing towards the fluorine, because any bond that fluorine is in, except when it's bonded to itself, is going to be polar, because it is the highest electronegativity. So it would have 6 dipoles, all pointing towards fluorine. So it would look a little something like,
Professor?
yep,
So the fluorines on the side, what are those called again?
equatorial,
So
and the ones on the top and the bottom are axial.
Okay. So when the equatorial are more electronegative, that's when it's polar?
Well, I'm just going to ask this question here. So I've got 6 polar bonds. Is this a polar molecule?
Mm,
I'm not sure.
no.
I got a no. I got an I'm not sure. Think of the distribution of those arrows. So each one of these arrows is exactly the same size, and they're all separated by 90-degree angles. So they're pointing in 6 different directions, and they're all at 90-degree angles from each other. So the question is that symmetric or is it non-symmetric?
It's symmetric.
It's symmetric. So if I have 6 perfectly symmetrical dipoles, all pointing in the same direction out, does that make for a polar or a non-polar molecule?
Non-polar.
Non-polar. That's right. That's exactly right. In fact, it's by using fluorine, you can make basically anything a gas. Like this is how uranium gets enriched. So uranium forms uranium hexafluoride. And so uranium, which is a metal, generally is not a gas. But you surround it with fluorines, and it becomes nonpolar molecule, and now it's a gas. And so it's a very heavy gas, but it's a gas. And so if you take this gas and spin it at extremely high speed in a centrifuge, you can separate the difference between uranium-238 and uranium-235. You can make a bomb out of 235. You can't make a bomb out of 238. So that's how you separate. That's basically how uranium is enriched to make bombs or to make nuclear fuel, is by turning it into a nonpolar gaseous compound by reacting it with fluorine. Anyway, fun little story to go with. Fun stories about fluorine. All right, so any questions about that? Now remember, one thing I want you to remember, that if you have a symmetric arrangement of dipoles that are all the same size, that is going to be nonpolar. So in other words, if you have this, they're all the same size. They're all pointing at 120-degree angles from each other. That's going to be nonpolar. If you have, in three dimensions, if you have one going backwards, one coming out, and then 2 in a plane, and they're all the same, again, pointing in the same direction, this time in a tetrahedral, also nonpolar. So anytime you have a symmetric arrangement, it's going to be nonpolar. Now, the minute one of these changes, let's say you've got this dipole changes from pointing out to pointing back in, that's no longer symmetrical. And now you have a net dipole pointing down. And so that will be a polar molecule. All you need to just substitute the atom. So this is carbon. This is hydrogen, hydrogen, hydrogen. If you substitute this, actually, let's point to the other. If I make one substitution, I change one of those hydrogens to fluorine, it becomes polar, just because I've changed the direction of one of those dipoles. It's not nonpolar anymore. All right. Any other questions? You want to do a couple more before we go? How about B? B is an unusual molecule you may not be familiar with. So B is I Cl2 minus. So you look at this and you go, that's a weird molecule. I mean, it's nothing but halogens. But remember, iodine is so big that its electron cloud is so large that a smaller, more electronegative halogen can start pulling electrons from it. And that's what's happened here. So iodine is bigger. So is it going to have a lower electronegativity than chlorine or a higher electronegativity than chlorine? They're both in the same group. One is bigger. So is iodine going to be more electronegative or less?
Less.
Less, exactly. It's bigger. So it can't pull on those electrons like it used to when it was young and small. Now it got big and old and fat. And so it can't pull on electrons like a young, fresh-faced chlorine atom. So we put the iodine in the middle, and we put chlorine on one side and chlorine on the other side. 1, 2. So how many electrons am I going to be dealing with here?
22.
I got 7 and 7 and 7, and the 1 from the negative charge. That's right. 7 plus 7 plus 7 plus 1, 22. So how many electrons are in bonds?
4.
4. So I got 18 left over. So first thing we do, decorate the outside atoms, make sure they get a full octet. Each chlorine has 2 from bonds, so we give them 1, 2, 3, 4, 5, 6 more. 1, 2, 3, 4, 5, 6 more. That's 12. That leaves us with 6. And then on the iodine, we give the other 6. So 1, 2, 3, 4, 5, 6. So let's have a look. How many, so we know the chlorines have 8. How many total electrons does iodine have?
10.
10. Is that okay?
It's below the second group, so it can break the octet rule.
Yeah, iodine's a big ass atom. It can have more, it has more than enough room for another pair. I think it's in group, it's in the 5th or 6th row. So it's big. So there's lots of room for an extra electron. So let's figure out where the dipoles, first let's figure out what shape it's going to be. That's probably a good place to start. What shape is that going to be? So when we do AXE, iodine is a central atom. And how many atoms are around it?
2.
2. And how many lone pairs are around it?
3.
3. So that's AX2E3. So we have 5 electron groups around the central iodine. That is which group? Which shape group is that? Or geometry group? Where there's 5 electron groups.
Trigonal bipyramidal.
Yep. Trigonal bipyramidal. That is indeed true. So that means we have 5. So where, that means we have 3 around the equatorial region and 2 in the axial. So since we have this particular setup, who's going in the axial and who's going in the pyramidal?
I'm just guessing, but I think since there's 2 axials and there's 2 chlorides, then the chlorides would go in the axials.
Right. Generally, the atoms go in the axial positions and lone pairs go in the equatorial positions. Because remember, there's 120-degree angles between the equatorial positions and only 90 degrees between the equatorial and the axial. So if you have something that's really repulsive, like lone pairs, you generally stuff those in the equatorial positions. So let's draw what that would look like. So I have my iodine in the middle and my chlorine on the top, chlorine on the bottom, and my lone pairs there, lone pairs there, and a lone pair there. Now, what shape is this? What molecular shape is that?
T-shaped.
No, remember, when we look at the molecular shape, we're only looking at the atoms. So atoms only.
So linear.
Right. That's a linear molecule. That is a linear molecule. Mm-hmm. Exactly. So that's what. So overall, the overall shape, the group that it's put in is trigonal. Now you're making me have trouble saying it. Trigonal bipyramidal. So these angles are 90 degrees, and these angles are 120. But then if we just look at the molecule itself, we don't see the electrons, we just see the atoms. And when we just look at the atoms, it just looks like it's linear. Yeah, so that would be a linear molecule. The group it's in is bipyramidal, trigonal bipyramidal, but the actual molecular shape is linear. And when I ask you this on a test, I will make sure I differentiate. I'll say which group is it in, and then what molecular shape is it? Okay, just to differentiate between the two.
Professor.
Mm-hmm.
For the lone pair to the right of iodine, do we draw that as a wedge or as a line? Like, does it matter?
Oh, basically, it doesn't really matter. Just have one with a, and usually we don't really draw the. We generally don't draw the lone pairs in with the shape. I sort of just want to show you in this particular instance where they would be. And so when you have this particular setup with the equatorial, you usually have one coming out, one going behind, and then one being in the plane, just to show you that there's three of them in a circle. It doesn't matter which ones you make. Which ones are going back, which ones are coming forward, or where you put them. The one on the left could be coming forward. The one on the right could be going backwards. It doesn't really matter. Okay, any other questions?
Yeah. So why doesn't this one have dipoles?
Oh, it is dipoles. So who's more electronegative, chlorine or iodine?
Chlorine.
Chlorine. So we would have dipoles. We have one going in that direction and the other going in this direction. So yeah, I want you to look up and see whether or not this is a polar molecule or a non-polar molecule. Be interested to see what you find.
Are we only considering the atoms when we're thinking if it's symmetrical or not?
Oh, it's symmetrical. Even with the you have to consider the lone pairs. That determines whether or not it's symmetrical. If there was another chlorine here, it would no longer be symmetrical. Then you would have the T shape or a seesaw, because then you'd have X3E2, and that would be T shaped. So you'd have chlorine, iodine, chlorine, chlorine. That would be a T-shaped molecule, and it would no longer be symmetrical. So it's the position of the lone pairs that makes it symmetrical. So I'm going to look that up myself, because it isn't simply, as far as the polarity goes, you add up all the dipoles, but then there's something more on top of that that's a little beyond this class. I'm just be curious to see whether you find people describing this molecule as polar or nonpolar. I'll look it up myself, because I bet you find two answers. So it might be something on a bonus someday, a mean bonus question.
Professor, there was a question in the chat, and I was wondering.
I should have been looking at it. Do we have to put the dipole arrows for all in number 3? Does it ask for them? Nope. Nope. We only put those in if it's asking for polarity. Now in number 4, what you're doing with number 4 is that's a table of basically all of the molecules you've drawn, and then it asks you whether they're polar or not. So you can go back and look at all the ones you've drawn and determine whether or not they're polar. But it doesn't say you have to. If you want to put the bond dipoles in, that actually might be helpful to you to figure out whether or not they're polar. But it's not necessary. Because if it doesn't ask to indicate the bond dipoles, you don't have to do that. But it will help you determine whether or not the molecule is polar. So
Okay.
Any other questions about number 4? Basically, number 4 just goes back and it's just fill in the blanks. It's like, which of these molecules that you drew, like look at, it has 5 atoms bound to the central atom with 0 lone pairs. Which one is that? And then you find out which one that is, and you just fill out the rest. What's the geometry? What's the shape? And then whether or not it's polar.
Is there like a pattern or any quick way to figure out if it's polar or non-polar, or do you have to draw it every single time?
Basically, if it's symmetrical, it's going to be non-polar. I mean symmetrical in every way. So for instance, if I have this is not going to be symmetrical because I have hydrogens on one side and I have chlorines on the other. So I have dipoles going in this direction toward the carbon, and I have dipoles going in this direction toward the chlorines. That is not a symmetrical molecule. So that is going to be polar, because basically if you add all the dipoles up, they're pointing in this direction. So you have a net dipole. So that is going to be a polar molecule. What you have to look out for is what's the difference in polarity. If they're really, really small, it won't be terribly polar, even if it is asymmetric, because the difference in electronegativities will be so small, it won't matter. But generally, most of these bonds are going to be polar. It's just a matter of how they're arranged. So if it's symmetrical, not polar. If it's symmetrical, not polar. If it's asymmetrical, it's probably going to be polar.
Professor.
That's the general rule. Yes.
So for recitation 7, 8, and 9, are those going to be due all at once, or do they have different?
7 and 8 will be due Thursday, and this will be due a week from today.
Okay.
Yep. So yeah, so don't worry if this is still a little confusing. We're going to go over more of this on Thursday. Get the rest of the class caught up and give us a chance to sort of review it with fresh eyes. But yeah, what I will do is I will put electronegativity table, which I should have done earlier. In fact, I thought I had until I looked and saw that I didn't. what I had done was put the link for the ptable.com and, figured, well, that's done. But what would be helpful is actually just have a reference sheet to look at, because there's a reference sheet like for tests and stuff that we give out that has that on it. In fact, I think that's in there. If the Chem 210 reference sheet, I think, does have a periodic table with all the electronegativities on it. I think it does. But even if it does, I will put another table with all the electronegativities on it. I'll make it a nice, colorful one.
Oh yeah, it does, Professor. I just seen it.
It does, right? But it's just plain. It's super plain. So yeah. So you can use that one, or I'll put a real pretty one. I like the pretty one.
Okay, thank you.
Yeah. Any other questions before we go? Is it clear about number 4? What you're doing? You refer back to all of the diagrams you've drawn, and it asks you about them. Like, where does this fit in? Where does this one fit in? Is it, what geometry group is it in? What shape is it? Is it polar or not polar? That sort of thing. And then basically just fit each one of them in there. If you have any questions about it, yeah, just I'll be at office hours Mondays and Wednesdays at 11, or just hit me with an email. Okay.
Thank you.
All right, everybody. I'll see you on either tomorrow or on Thursday, where we're going to talk about this again. So if it's bending your brain right now, don't worry too much about it. We're talking more about it at length on Thursday, because it's really important to understand polarity when we start talking about how molecules interact with each other, because that's a whole chapter in and of itself. And so if
I have
you
a
don't,
question.
yes.
So for nitrogen dioxide,
Mhm.
does it has a radical?
Nitrogen dioxide. So 6 and 6, and just nitrogen dioxide, no charge.
No charge. Yeah.
Yeah, it would have, yeah. So 1, 2, so that's would be 13. Let me go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 1. Yeah, that is an odd number of electrons, so that would be a radical.
So why would it do this?
Because there's an odd number of electrons.
Okay. So I mean, why would it be stable for this molecule?
If it's symmetric, it finds a way to be stable. Well, radicals aren't really stable. I mean, they're not stable for super long time. I mean,
Okay.
eventually they do react with something.
Okay.
So this would always be trying to react with something then, like just constantly trying to get to the...
That lone electron is desperately either want to give it away or grab another one, depending on, in this instance, nitrogen's got 1, 2, so that would go there. That would go there. No, I can't do that. So this would be negative, this would be positive. And then, that nitrogen would definitely be trying to steal an electron from somebody to make nitrite ion. That's stable. And so when it took another electron, then the nitrogen would have a lone pair and 3 bonds, like nitrogen always does. So that'd be a much more stable arrangement. So you take that one electron away, it becomes very, very reactive.
Okay, thank you.
Yeah. That's why one of those things, I mean, this is like one of the things that's produced in car exhaust. And that's one of the things that your catalytic converter does, is to cut down on the amount of this particular thing forming, because it is so reactive and nasty. Basically, you want to avoid nitrogen oxides as much as possible. It's one of the things that when you go get your car smogged, it's measured how many like NO and NO2 compounds are formed. You want to keep those super, super low. All right. So if there are not any more, other questions, I will see you guys. Do we have to put all the, oh, I already did that one. Yeah, for number 3, you don't have to include the dipoles. If they're not asked for, don't. But it might be a good exercise to show you whether or not the molecules are polar. Because like on a test or something, I'll ask you, is the molecule polar or nonpolar, and explain. So the explanation will be, you know, adding all the dipole moments up and seeing that they point in one direction or another, that they don't cancel each other out. So you don't have to, just to answer the question. You don't, that's not necessary. Okay? All right, everybody. Ooh, it's late. No, not really. We have time. But if anybody does have anything else, we'll call it a day. I'll get some more tea, and I will see you tomorrow or on Thursday morning. Okay?
Okay. Bye-bye.
All right. Bye, everyone. Stay well.
Bye. Thank you.
All right. Thank you.